Hi. Uh, today's topic will be variational autoencoder. Now, I know that there are quite a few really good lectures about variational autoencoders that are available online. One of the very good lectures, I would say, is by Allat Kumar. But uh, there are some, in some lectures there are some certain parts of variational autoencoder has been covered. In some of the lectures they actually bring another perspective of variational autoencoder. So what I want to do in this particular lecture is that I want to amalgamate all these kind of different concepts, and I want to actually collect all of them to make it one concrete lecture on variational autoencoder. Is one of the very important deep learning models that has been actually is very actually have become very popular, especially learning the latent representations. This model is doing something really cool. So let's start. Yeah, and if you have some any problem or anything, just mention that in the discussion section. So let's start. What is a variational autoencoder? So we will start from this particular graph, uh, Bayesian graph. So this is called a Bayes net. So the z's are the latent variables, x's are my observations, and from this z to x, this particular h denotes the observed distribution, and when I'll go like this thing is the z given x, and this is something called inference. Okay, so our main task is to calculate this particular guy, or to estimate this particular guy. Now x can be rd, z can be some r, I don't know, it's like d1 is not equals to d2. Okay, so and this is, and we are working actually in a unsupervised setup. We don't have any access to the actual labels. So in this setting, our job is to estimate the patterns within our data points x. So this x is nothing but something like this: I is 1 to n, and every xi is rd. Okay, you can also see some kind of a box diagram and 1 to n and all this kind of stuff, so I don't want to go into that zone. So what our main job is actually want to estimate two things. First, we want to estimate this particular inference, or as this is a unsupervised setup, we want to know, or we want to estimate the density of the data point. So by that what I mean is that each of these x, if each of these x is actually sampled from a probability distribution p of x. So what we can do, we want to estimate this thing. Okay, so this is called something called maximum likelihood estimation. So we can write like this: max theta, or we can do something like this: log px. This is called maximum likelihood estimation. or so okay, or we wanna calculate this thing. Okay, so these are the two things that actually will lead us to the same result which we will gonna derive. But what I'm trying to say is that we can start from this thing or we can start from this thing. Okay, so now one of the things, like this quantity, so if I write like this, p of x, this quantity can be written something like this. I'm sorry, it's not, it is xz dz. Okay, and this is also xz dz, this is z. So I just marginalized, it's a simple probability product rule. So I just marginalized with respect to z. Now if I come here and if I do some bit of algebra, so this can be written as this is from Bayes rule, and here also we will get the same thing. Now calculating this particular integral is hard. Okay, why? Because what happens is that this z's are d1 dimensionals, so we may have like dz1 z2, so this integral can grow in a large number, which is actually difficult to integrate, because if it is like d1, then we may need to integrate d1 number of integrals, which is a NP-hard problem, and we cannot do that basically. So this integral is actually hard to calculate, and here comes the thing which will help us to get away from this particular difficulty. So that is called variational inference. Okay, now why it is called variational inference? Because okay, so let me I'll tell you why it is called variational inference. So we are not able to calculate this guy. Okay, so in terms, what we can do, we can have a known distribution which is qz given x. Okay, now when I'm saying that this distribution is known, it means that this distribution's type is known. I mean, it is generally considered to be a normal or a Gaussian distribution. So I can write something like this, or even I can do like this, or it's better that let's keep it simple. Okay, so this is a Gaussian distribution, and these two things, they are unknown to us. So this is the mean, this is the covariance matrix, because I am considering it to be a multivariate Gaussian. So these two things are unknown, and we have to estimate these guys. Okay, so that's why it is variational, because what I am actually trying to say is that we don't know this posterior distribution or inference, whatever it is, whatever you can call it. This can be also written, it is also posterior. Okay, and this thing, sometimes it is called evidence. Okay, so it is like posterior, this is the prior, this is observational, and this is evidence. Okay, so we don't know this guy or its type, it may be a mixture of Gaussian, it may be a chi-square. I don't, we don't know this what type of distribution is this, but we know the type of the distribution of this guy, but we don't know its parameters, which you can estimate. So basically what we are actually trying to do is that we want to take the difference between these two guys and we want to minimize this guy. So you can say that in a typical supervised learning we have got some x and y, and also we have some predicted value, and what we try to do is that we try to calculate the difference between the predicted and the target, and we want to take the expectation and we want to minimize, right? So here also, so though these two are different, but you can take an analogy. So what you can do, or how you can think about it, like this guy QZ, I'm sorry, this guy is our predicted and this is our true, and we want to minimize the difference between these two distributions. Okay, so remember, their y and y hat, these two were real numbers. Okay, but these two are distributions, and we want to minimize the difference between the two distributions. How we can do that? So there is a family where we can take the difference between two distributions. One, in one of these we can take the difference as minus sign, and in another one we can take the difference as the ratio. So for example, if I have got this is target and this is my predicted, so I can have something like this or I can have something like this, and both of these two terms can give us the relationship between the difference, how similar or different my original and my target values are, right? So in terms of difference, in terms of distributions as well, we can have these two things. So when we have this division, we have something like this. So this is unknown, I'm sorry, this is not unknown, this is predicted, this is true, and we can have something like this. I'm sorry, QZ given x minus BZ given x. So we will obviously, with variational inference and variational autoencoder, we will use this particular form, but let's at least talk about this form, because this is also very, very important. This form is sometimes called integral probability metric. Okay, and so what we are actually trying to do, we have some distribution and we want to predict a particular distribution, and we want to minimize the difference between the predicted and the true distribution. Okay, so there are two particular distance metric which can be used. One is called Wasserstein. This is also sometimes called as earth mover distance. Sometimes we also impose a gradient penalty or a one Lipschitz constant. I'm sorry, it's constant. And also we can also estimate the difference between these two using another distance metric that is called MMD. This is called maximum mean discrepancy. Okay, so what are those things, how we can do it? I don't want to discuss this in this lecture, but I just want to give you some sort of like a brief overview that this is not only the form where you can calculate the difference between two distributions. We can calculate the difference between two distributions using this using the minus sign as well. Now this division is actually in statistics or in machine learning or deep learning, this is not called as difference, this is called divergence. So when I'm taking the difference, generally it is taking as a mod value. So we can flip these things up and things won't change. But this divergence thing, so this guy is not equals to this guy. Okay. So there are generally two kinds of divergences are there. One is KL, another one is JSD. Actually the thing is that, like, I can give you another thing, like, so this thing, so this divergence can be estimated, sorry, using KL or using JSD. JSD is nothing but an average of KL, but yeah. But actually the thing is that why we need the integral probability metric or IPM is that there is a problem with these two with these divergence measures. So when we are actually taking when actually we will take gradients, these two things will create problems at the very beginning. And that's why, to rectify that or to minimize that problem, we actually want to use IPM instead of this divergence matrix. But in variational autoencoder, we will use divergence. Specifically, we will use KL divergence. Okay, so let's write the KL divergence between QZ given X and PZ given X. Okay, now I told you that this QZ given X is nothing but a normal distribution or a Gaussian distribution. So what I can do, so I can specify this phi, and this phi is nothing but the set of parameters that we want to learn. So this mu and this sigma, they are also parameterized by phi. Okay, so what is phi, how it will how it will come into the picture when we will train, we'll discuss all those things. But let's do a bit of algebra. So what is this KL? This KL is nothing but, this is an expectation term and a log term and a division term. Okay, now what we can do, we can, okay, so I'm doing this in terms of integration, in terms of PDFs. You can also replace this integration with a summation, and you can take this as a PMF, and you can also do the same stuff. But ideally, in a general case, we should do this using integration. So yeah, so let's do it. So this is nothing but, I'm sorry, this is nothing but QZ given X log QZ given X minus log PZ given X. This is big bracket and this is DZ. Okay. Yeah. Now if I expand these things, so this is QZ given X DZ minus another QZ given X log this thing, the small thing PZ given X. What is this thing? We can write like this. We can use base rule. We can flip things. PZ PX DZ. What is this guy? This is an expectation where Z is sampled from this probability distribution, and we have this thing. I'm doing a bit faster because I hope that these notations are clear to you guys. So yeah, and there is this negative sign. So this is have I done some mistake? This is qz given x. Yeah, so this is this. I think okay, let's not do this. Okay, let's not do this. Okay, so let's keep it here. Let's keep this thing as it is, and then I have my qz given x. I have log p x given z and minus q z given x log pz plus qz given x log px dz. So basically what I'm doing is that this thing is nothing but log this plus this minus this, and I can expand this thing. Okay, so this whole thing is actually written by this 1 2 3 three terms. Okay, so now what I'm doing, I'm taking this and this together. This is qz given x log z given x divided by pz, and this is dz. Okay, this is minus, I have qz given x log px given z, this is dz. Okay, and then I have something like this. So here I can take this log px out of this integral, because this internal integral actually doesn't depend on x. So this is qz given x dz. Okay, so okay, so now this thing is an expectation. So this thing is an expectation with respect to this probability distribution. Okay, oh, I'm sorry, this is, I think I missed it. So there is a q, there is a q, there is a q, and this is qz given x pz minus, this is also an expectation, and this is only log p of x, because we are taking an integration with respect to a density, and this internal term will be 1. Okay, because if I have got some probability distribution p of x, if I sum it up, this is 1, or if I have got some conditional distribution, x is sampled from, say, x given z, then also this thing will be 1. Okay, so this is nothing but a conditional distribution, and we are integrating out of it, so this will be 1. Now, important, this expression is very, very significant, and this is, so we actually started from this guy, and we did some bit of algebra, and we came to this. So I am writing it, qz given x and some pz given x is nothing but This is expectation. Z sample from this distribution. This is log qz given x divided by pz minus another expectation, another log, another. Okay, cool. So what is the significance of it? Now what we are trying to do, so this is our target, again this is our predicted. So our job is to minimize the KL between these two distributions, right? And in terms of what? So our job is to minimize this guy. Now here are some of the things. So this qz given x, I told you that this qz given x is a Gaussian distribution with a mean mu and a covariance matrix sigma, which are parameterized by phi. So these q's are nothing but a function with the parameters phi, and this z. So generally we take this distribution. So these z's are actually sampled from this probability distribution, which is ideally a standard normal distribution. So this is also known. Okay, this p of x, this guy is again intractable. We cannot calculate this, but this is an observed distribution. You remember, this is our diagram. So if I draw it here, so this x given z is an observed distribution, right? So this is also observed. This is the data that we generally saw in our data set. So this distribution, so we can also estimate this particular distribution. So this distribution is generally parameterized by theta. Okay, so this whole equation, so this entire equation from starting from here till here, we have got two parameters, phi and theta. So when I say that we want to minimize the KL divergence between my variational posterior and my true posterior, what I'm trying to say is that we want to minimize the KL with respect to these two parameters, and this is phi and theta is somehow here. Okay, so I hope till this part it is clear. Now this quantity, this expectation, okay, so this expectation, this quantity actually depends on phi. This quantity depends on both phi and theta, but this quantity is independent of theta and phi. So I can write something like this: log p of x is nothing but the KL of this guy minus, so I'm writing like this is plus, I'm placing this expectation term, the second expectation term. So this is nothing but qz phi z given x log p theta x given z minus expectation q phi z given x log q phi z given x pz. Okay. Now what we are trying to do, this guy is independent of theta and phi, and our job is to minimize this guy. Okay, yeah, our job is to minimize this guy. and my right hand side, sorry, my left hand side is independent of the parameters, and we are minimizing this scale divergence. So it means that to make the left hand side this thing constant, we have to maximize this whole thing. Okay, we want to maximize this this entire thing, and sometimes this entire thing is often called as elbow. Now why this is often called as elbow loss? Because because our KL divergence our KL divergence is greater than equals to 0. So this quantity is greater than equals to 0. It means that this quantity is also greater than equals to 0. Okay, and so if I write this, that my expectation, now I am not writing as z or something like that, it is qz given x pz minus expectation log px given z plus log px. This is also greater than equals to 0, which means that log p of x is greater than equals to expectation log pxz minus expectation log qzx pz, which is ideally this whole term. I'm sorry, this whole term is nothing but this term, and this is called elbow loss. Okay, so you will often see that people will say that, you know, we try to minimize the KL divergence, which in turn will say that maximize the elbow. Okay, so this is the thing. Now you may ask me that that why this maximization will occur. So why this thing actually help us, because we are trying to minimize this guy, which in turn, which we can write like this, log, which is independent, is equals to KL plus this is independent of my parameters, and we want to minimize this KL, and this term is, so we want to minimize the KL. My left hand side is independent of my parameters, so we are saying that we can maximize this elbow. Now there can be another interpretation of this loss. So in the very beginning, I say that our starting point can be this from the posterior or from the marginal. Okay, or the marginal, this maximum likelihood estimation. Now if I start from this marginal distribution, and this marginal distribution has a lower bound, which is this, our job is to maximize log p of x, but we cannot do that. Why? Because this log px is nothing but log, this log px is nothing but log p of x given z dz. Yeah. Okay, so as this internal quantity is intractable, we cannot do this maximization, but this log px has a lower bound, which is this elbow loss, and if we maximize this elbow loss, which will in turn help us to maximize this guy. So our objective will be satisfied if I maximize the elbow loss, which in turn will maximize my marginal or my maximum likelihood estimation. Now why? Okay, one reason is, of course, if we come from this posterior distribution, if we come from the scale divergence, of course, the scale divergence is nothing but the scale divergence. If we do a bit of algebra, this marginal distribution is nothing but the summation of the scale and this elbow. So this is independent. The left hand side is independent, and we are trying to minimize the KL, so we want to maximize the elbow. So this is one fine, but this can also be explained from another particular thing in statistics or in mathematics, that is called Jensen's inequality. So in a Jensen's inequality, if we have a function, if we have a concave function like this, and if somehow if we have a concave function like this, and if we somehow will be able to find a lower bound of this concave function, and if we maximize this lower bound, which will actually help us to touch the optima of this concave function. So I'm not going into too much details, I'm just giving you an intuition. And so this concave function, so this log is nothing but a concave function. Okay, so this log is a concave function. We can use Jensen's inequality, and which will help us to give this particular elbow loss. And as our job is to maximize this guy, this log, which we can do that by maximizing this elbow loss. So this is the loss function of variational autoencoder. So we actually started from here. This is my variational posterior, this is my true posterior. Okay, we want to minimize this guy, which actually in turn we have to maximize theta phi some elbow. Okay, this is called as elbow, which we can write like this. This is an expectation where z will be sampled from z given x, yeah, log p theta, this guy, minus, again this will be sampled from this expectation z given x pz. Okay, so this elbow can be also written like this. This expectation is same. So I'm just writing this expectation here minus this expectation. It is nothing but an expectation, and then a log with a divergence term. So this is nothing but a KL divergence. Okay, and this is also phi. This is also phi. Now, why this particular loss function is having these two terms? One is this, another one is this. You can watch the video of Allat Kumar. He actually explained in a very detailed way by using the graphs. So I'm not going to that direction. I'll give you another perspective of it. So first, now let's think about like where neural network will help us. Okay, where we can use neural network to maximize this particular loss function. Okay, see, in a typical deep learning or in a typical machine learning, what we need to do, we need to have we generally, in a statistical learning theory, we always try to formulate a risk. Okay, this is called risk functional approach. So we have a risk which will be parameterized by h, and we need to optimize with respect to h. This is often called loss function. So in a machine learning or deep learning, the first building block is the loss function, and we have got our loss function. Now what? We have got our parameters. So what we need to do? We need to optimize this particular loss function with respect to these parameters. So what do I mean by that? We need to take the gradients of this loss function with respect to these parameters, and we need to do gradient descent. But we can use various kind of models. Here we will use deep models or neural networks. So where neural network will come? So we can see that this is a, so here if you closely observe, this function is known z sampled from pz, which is a standard Gaussian distribution. These two functions, this function and this function, these two functions can be replaced by a neural network. Why? Because we know that neural networks are universal approximators, so they can be able to approximate any kind of functions. So of course they will be able to approximate a probability density function. So this thing is a neural network, and this thing is also a neural network. Okay, so I told you in the very beginning that q phi z given x is a Gaussian distribution with mu and sigma as parameters. Now this mu is parameterized by this guy, sigma is parameterized by this guy. What do I mean by that? What I'm trying to say is that you have a neural network which will take the input as x, and it will give you two outputs. Okay, let's draw it. So I have a neural network. This neural network is parameterized by phi. I'm giving one x. There is one output head which is mu. There is another output head which is called sigma. This is phi. This is parameterized by phi. Okay, now my z or my latent code will be sampled from a Gaussian distribution which is parameterized by this mu and this sigma. Okay, so it can be easily done in a typical code using PyTorch. What we can do, we can have a bunch of feed forward neural network layers, or we can have, like, if we want to use this for a image data set like MNIST or CFAR, we can use CNNs or whatever it is. So the important thing is that we need to feed my data points x. So this will be my actual data distribution or my training data. I'm feeding this in a bunch of networks, and that network will spit two particular things. One is the mu, another one is the sigma, the mean and the standard the covariance matrix of a multivariate Gaussian distribution. And from that Gaussian distribution I'm sampling. So this thing, this guy is nothing but this guy. Okay, now from here this z will be fed to another network. Let's draw it like this, and this network is parameterized by theta. Okay, so z will be fed to another network, and this network will output some x hat. Okay, and this network is nothing but this is sampled from a probability distribution of theta x given z. Because I'm feeding z, I'm getting x, and my network is parameterized by theta, and this is my reconstructed output corresponding to this guy. Okay, so this is why it is called variational autoencoder. If we don't have this mu and this sigma, we'll be having a standard autoencoder, but again, that is a different topic. I don't want to go into that, but this is why it is variational autoencoder, because this autoencoder has a probabilistic a probabilistic thing, or a stochasticity in it, because the z's, they are not a vectors, they are random vectors which are sampled from a normal distribution or a Gaussian distribution. Okay, so this is where actually a neural network actually comes into picture. Now you can be able to easily code this in PyTorch or in TensorFlow or whatever it is. So this part is often called encoder, this part is often called decoder, and this is where it is actually going. So if you see that this particular loss function, this KL divergence, now this thing is a normal distribution, this is a Gaussian, this is also a Gaussian. So the KL divergence between two Gaussians, it is a well established, it has a closed form solution, so it won't be a big challenge to calculate these two KL divergences. Now this quantity, this expectation over this P of x, this particular guy is nothing but, so this is nothing but x minus x prime. So this is often called the reconstruction loss. Okay, so why it is called a reconstruction loss? Because this distribution we can also think as a normal distribution, which will be having some mu and some sigma. So if it is a multivariate Gaussian distribution, so the form is like this, so it is like 1 by z, this is a normalization constant, and this is x minus mu1, I'm sorry, it is like x minus mu1 transpose sigma inverse x minus mu1. We often take this sigma 1 as an identity, so this will go away. So this is a transpose, so x minus mu1 transpose times this, so this is nothing but an inner product. Okay, so this is nothing but a inner product or an L2 norm. Okay, so this mu1 is so this is like x hat, this is like x hat, and so yeah, sample, I'm sorry, it's not like this, this is x, this is x, because my x will be sampled from this distribution, so this is x, and this mu1, this is nothing but my x hat. Okay, this is nothing but my x hat, which is actually coming out of this guy. So basically what I'm actually trying to say is that you are nothing but estimating the mean from this decoder. From the encoder we are estimating both the mu and the sigma, but from the decoder we are estimating the mean, and if we feed this mean into the normal multivariate Gaussian distribution equation, this guy will ultimately become something like this. Okay, so actually, so I would say empirically, so this is empirically, this is theta, this loss function, will look something like this. It's 1 to n. This is xi minus, this is the reconstructed output, minus the KL divergence q phi zx pz, or we can, so this is xi. Now what is this x hat? So first what we are doing, we have this neural network q phi, right? We have this neural network q phi, which is taking an input x, it is producing some z, and then we have this neural network, okay, minus the KL, sorry, KL, this, okay. So this is copy of this term. So this is the empirical loss function. So what you need to do is that, I want to copy this thing, not the empirical, the actual theta phi. So this is expectation, this is z, this is q phi z given x, and this is log p theta, this is x given z minus KL of q phi z given x pz. Okay, so I think I didn't do any mistake. I have a tendency of doing silly mistakes. Yeah, and our job is to minimize theta phi L theta phi. So what do I mean by this? So sorry, it's not minimize, it's maximize, okay, because this is the elbow loss, right? So this is the elbow loss, or rather it is like minimize theta phi minus of this elbow loss. So it means that what we need to do is that we need to calculate the gradient with respect to these two guys. We need to set it to 0 and we need to do the estimation. Now these two things, when we are trying to take the gradients of this loss function, there will face a particular problem, and we need to overcome that. It's not so simple to take the gradients. How? Let's take the gradient. I'm sorry, I don't know why this is happening. Okay, so let's take this gradient first with respect to theta. Okay, so network wise it's very simple. Okay, so this is this, then I have another network, there is my x hat, this network is for px given z, this is z, this is x, this is qz given x, this is phi, this is theta, this is mu, this is sigma, and this is that. Okay, so this is my simple VAE. So I need to do, I am actually taking the gradient of this loss function with respect to the parameters of the decoder. Okay, let's take the gradient. So if I do this, now this expectation term, so this expectation term, so okay, let's do step by step. So this is a minus, so I have something like, I'm sorry, I have something like this, expectation z q phi z given x log p theta x given z minus the gradient of this KL divergence. Okay, simple. Now first have a look of this particular gradient. Now this gradient is actually 0. Why? Because this scale term doesn't depend on the parameters theta. So this whole thing is actually 0, so we can straight away ignore this. So I can remove this. So now this is, now what we are left with is this particular term, and in this particular term this expectation is nothing but some summation, right? So if I say expectation of x, it is nothing but x px, right? So this is nothing but summation. So suppose I have got this, like, so this p of x, this probability distribution is actually parameterized by theta, and I am taking a derivative of this guy. So I'm taking a derivative this guy. So it means okay, I'm sorry. So okay, so leave it. Okay. I think I actually got a ping. Let me quickly reply to it. Yeah, so if I take the derivative, it is simple. I can push the derivative inside this. Okay, so I can, what I'm saying is that I can, so when I'm having a derivative outside of an expectation, I can push that derivative inside of it. Okay, so this is what we will actually do. Actually I actually have done a mistake. It is not like that. So suppose I've got an expectation of fx, yeah, fx, and this fx is actually parameterized by theta. Now this guy is nothing but, this thing can be written as this. Okay, yeah. Now I'm taking the derivative of this, which is nothing but, because this thing is nothing but, this is like x1 f theta of x1 plus this. So this is I'm sorry, this is not like that. This is this thing and the distribution, and this is f theta of x with p of x, and here it is d theta, which is nothing but f theta of x px, and this is nothing but the expectation of this. So what I'm trying to say, is that what I'm trying to say is that, okay, I think I got another ping. Yeah, no. So what I'm trying to say is that when I'm taking the derivative of an expectation where the distribution function is parameterized by some other parameters, I can push this derivative inside. You can see this grad theta can be pushed inside, because this distribution x is parameterized by some other parameters, and this thing is nothing but this same thing is actually here. Okay, so this guy, now I can write theta L theta phi. So I can push this expectation inside of it. Sorry, I can push this gradient inside of it. So this is theta log p theta x. Okay. Okay. So this is cool. Now this expectation is nothing but just a summation. Okay, so this thing, I told you that this log, this particular term is nothing but x minus x hat square. Okay, yeah, so this is x minus x hat square, and so you are basically trying to do this, and here this x theta is actually parameterized by this. So this gradient is this gradient can be taken very easily. Okay, so this will be having an analytical form, so we won't be having a problem. So when we will do gradient descent, it won't be a problem. So empirically it can be written like this. L2 norm 1 by n, I is 1 to n. So this is the Monte Carlo approximation. This is this, and here is my gradient. Okay, so it won't be a problem. Now what about this gradient? What about the second gradient? Let's do it. So again, if I change it to here, so I have got this setting. Okay, now I want to take this guy as this guy, and I want to remove this. Okay, so what about this? This time I cannot push my gradient inside of it. Okay, so this thing, so what I'm trying to say is that this thing, so this is v phi f theta, this is x1 p phi x1 plus dot dot dot. So this guy is x1 phi x1 dot 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 dot. So this is something like this. So this is f theta xi. Okay, this is phi, this is xi, and this quantity first, this is a function of a random variable. This is not a probability distribution, and this thing is also not a probability distribution. So we cannot say that this whole thing is some sort of an expectation. Okay, so expectation of some function where the gradient will be inside. So the bottom line is that we cannot push the gradient inside. Okay, so again, if we actually started from this f is parameterized by theta, and this is the probability distribution, and we are taking the gradient with respect to the parameters of which this probability distribution is parameterized by. And here is the problem. Earlier it's not like that. Earlier, if you look at this, so this theta and this phi are different. So we are not taking the derivative with respect to the parameters of the distribution, but here we are doing the same thing. And we did a bit of algebra, and we saw that this gradient is nothing but, so this expression can be written in terms of this expression, and neither this guy is a probability distribution and neither this guy is a probability distribution. So this summation is not an expectation. So we cannot push my gradient inside of my expectation. And this is the problem of I'm sorry, this is the problem of like taking the derivative with with respect to phi. So 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 we have the loss function. Okay, so let me write the loss function here again. Theta phi is expectation q phi zx log p theta xz minus kl q phi z given x pz. Okay, so this time we are taking the gradient like this. Okay, and we cannot push my gradient. It won't have something like this. Expectation of q phi z given x, this gradient cannot be pushed inside like this. Okay, we have to do something, we have to do something. So this something is actually called parameterization trick. Okay, so we think that, I'm sorry, I'm not thinking. So what we will do, we will have some epsilon, which is a standard normal Gaussian distribution. Okay, and now this thing, this particular thing can be so yeah, so this thing, now my z, sorry, my z is this guy, right? And what is this guy? This guy is nothing but a normal distribution, right? So I can express my z in terms of my epsilon. How? Sorry, I think it is like this. Oh no, I think this will come first, then an inner product, and this is the element wise product, and this. Okay, so this is like if I have, so this is, yeah, if I have some m, which is a normal standard normal distribution, and some n, which will have a mu and a sigma square. This is in 1D. This n can be written like this: m mu plus sigma square. Is it so? No, it is not. It is mu plus m sigma square. So we can scale and we can do a affine transformation. So this is also called an affine transformation of Gaussian distribution. So yeah, okay, so this is what we try to do. I think this is not sigma square, this is also sigma, again mu sigma. Okay, so this is what we can do, right? So now what we can have, if z is sampled from this thing log, so what I'm trying to do, I'm actually trying to reparameterize this term, because see, when yeah, so I'm basically trying to reparameterize this term. And also you have to remember that this scale divergence, this is also an expectation. This scale divergence is also an expectation with respect to this distribution. So here actually is a bit of trick that we have to follow, this reparameterization trick. So let's see how we can do that. So this is log p theta x z. Now what we can do, this z's can be transformed as some epsilon from a standard normal distribution. This p of this guy is nothing but this guy, and this is log, this is p theta, this is x, given my z. Z is nothing but this mu plus the sampled epsilon this thing. Okay, cool. So empirically this thing can be written, so we can sample from the standard normal distribution L times, L times. So this is empirical, L is 1 to L log p theta, and this is x mu plus this L, or let's write it here. Okay, so now if you look at, px given z, and this is, yeah, so now if you look this term, this doesn't have a phi into it. Now we can take the derivative with respect to phi. Okay, because so now we can take the derivative, because you have to remember, you may ask me, where do you want to take the derivative, because this x, so when you will be having this x given this thing, so this first term, I told you that this first term is nothing but, so let me write it for you. So this log p theta x given this guy is nothing but x minus the reconstruction, right? And this x prime, what is this x prime? This is p of, I'm sorry, this is p of x given z, right? So this is actually sampled from p of x given z, or you can also say that this is my mean, right? So this p of x given z is a normal distribution with a mean of this and variance of this. Okay, so let's don't write like this. So and what I'm trying to say is that, so you're feeding your z. Now how do you get this z? The z's are sampled from a Gaussian distribution of this thing. So you remember that this is mu phi, this is sigma phi, this is phi, this is x. Okay, and your z's will be sampled from this mu and sigma, right? So when you take the derivative, with respect to this guy, it means that you have to take the derivative with respect to, suppose this will be 2x minus x hat, then there will be a minus sign, and then I'm sorry, it is not this, this x hat. Okay, and this x hat, this x hat has got this mu phi and this sigma phi. Okay, so this is actually called reparameterization trick, because we cannot take the derivative with respect to phi, because my probability distribution is parameterized by phi. Okay, so what we do, so what we did, we actually kind of changed the z's, we kind of expressed these z's in terms of these epsilons, which are actually sampled from a Gaussian distribution, a standard Gaussian distribution with zero mean and a unit variance. And when we can sample like L times, we express these z's in terms of these epsilons, and then we can take the derivative with respect to phi. Okay, and earlier we showed that derivatives with respect to this theta, that won't be a problem, right? That won't be a problem. So this is what it is called, variational autoencoder. So if I just do a summarization, if we just do a summarize, so this is like this. So this is my x, this is my encoder parameterized by phi, this is my mu phi of x, this is my sigma phi of x, and a z will be sampled from a Gaussian distribution. Okay, and so you can say like this. So ideally now the picture is a bit different. Okay, so ideally I have some epsilon. Okay, I have got some epsilon, I have got some, I've got some epsilon, and my z's are nothing but mu phi plus this epsilon times this. Okay, I've got some epsilon, some other. So this network will give us the mu and the sigma, and after we get the mu and the sigma in the forward propagation, we will be sampling some epsilon from a standard normal distribution, and we express our z's, and then we feed this z to another network which is parameterized by theta. We try to reconstruct this x prime, and we do a MSE between these two guys, and we have a KL divergence which will act as a regularizer for this particular network between this distribution QZ given X and my prior PZ, which is nothing but another normal distribution. Okay, so this is a KL. Okay, and these two are my loss function. So during my forward propagation, I'll be going from here to here. Okay, so I'll be feeding the X to my network, I'll be getting my mu, my sigma, I'll get my z's in terms of mu, sigma and epsilon, I'll feed that z to this decoder, and I'll be getting this x prime, and I'll calculate the loss, which will consist of this MSE term and this KL term. Easy, simple. This is my forward propagation. And then just because we did this particular thing, this reparameterization, we will be able to take the derivatives and do the back propagation. Okay, so during the back propagation, we will be able to take the derivative of this and the derivative of this. Okay, so this is in short what is called variational autoencoder. If you have any questions, please write it down in the comment section or in the discussion section, whatever it is. So thank you guys, thank you.